So now that we know how to use linearity, in particular superposition principle or additivity for each one of those op-amp building blocks, amplifier building blocks, we can combine them. So inverting summer. If I have VP is grounded, and then I have VN still has its feedback, but then I split this off into two separate components, two separate inputs. So I'm feeding this side with V1 and I'm feeding this side with V2. That's the same thing as if I drew something like this, but it takes more time to do that. More time to explain it, but now that I've explained it, I won't have to do it again. So we have VP here, we have VN here. V out by the superposition principle, because it's a linear circuit, it's V out due to 1 plus V out due to 2. So what is V out due to 1? V out due to 1 is if I turn everything else off, and everything else in this case is just V2, because that's all I have. I have V1 and V2 powering the circuit. I can ignore the power, the supply is going to these guys because they're not part of the analysis. I know that this defines the amount of headroom that I have on both ends, so I have to design within that range. I have to design within this range here. But notice that that doesn't affect the linearity of my circuit. Right? I mean, as long as I'm not hitting the rails, in other words, as long as my signal is not distorted. If I had designed this around a gain that was so large that I distorted, then it went like this, then that's a different story. Now all of a sudden I'm no longer linear. So the rails don't come into play when you're designing a linear system, a linear circuit, as long as you are operating within the range. So your output doesn't go beyond that range. So everything else about this circuit, if as long as all the components operate linearly, then V1 can be considered by itself, ignoring V2. So we have, if we're ignoring V2, not ignoring it, but setting it to 0. So turn on only V1, set V2 to 0. If V2 is 0, that's 0 volts. That means it's grounded. So remember that VP always equals VN. That's because of negative feedback. IN always is 0. That's because it's an op-amp. So no current here, no current here. These two values here are coupled. So that means VN at this point in this circuit, VN has a ground there. It's got a virtual ground because VP is is actually grounded. So if I'm grounded right here at this node, this whole node here is 0, and this value here is 0, then watch what happens when I consider the current here. Current comes down here. This is the current that I'm considering coming out of my output. Then normally you would expect this current to branch off two different ways, right? But in order for there to be a current across a resistor, there must be a voltage drop across that resistor. Because without energy that has to be dissipated across the resistor, you're not going to get a voltage drop. I mean, you're not going to get a current. Without any energy to drop across the resistor, there will be no current. So there is no energy across this resistor because it's at the same potential on both sides. It's at 0 here and it's at 0 here. So this current is 0, which means we can just ignore this entire side. We can ignore the entire branch right there. Then this current just goes all the way through. So this should remind you of the inverting amplifier. Just by itself, this is an inverting amplifier. Without V2, it's an inverting amplifier. So what is the gain term for the inverting amplifier? Well, we have the input, in this case it's V1, times the gain term, minus RF over that resistance down there. In this case it's R1. So in the same argument, because V2, the branch V2 that's over here that I erased is just a mirror image of this branch, then the gain term is going to be a mirror image. So it's going to be gain on V2, and then it's going to be the same minus RF, but this time the R2 resistor that I've erased. So there's your inverting summer. It's just a sum of these two terms that I've calculated here. Difference amplifier. Now we have V something on this side. We always have negative feedback. We have so we have V1 on the non-inverting side. We have V2 on the inverting side. V out, because it's linear in the sources. It's linear in the inputs. V out is V out due to 1 plus V out due to 2. So V out due to 1 is V1 times its gain factor. And you'll remember the gain factor, because we're turning V2 off. With V2 off, this circuit looks exactly like the first circuit that we analyzed, the non-inverting amplifier. So that's 1 plus RF over R1. Then V out due to 2, that's when we turn V1 off. We turn V2 on. With V1 off, we're grounded there, and this is identical to the inverting amplifier. So it's V2 minus RF over R2. Summing difference amplifier. So we're going to sum the inputs on both locations, and we're going to find the difference between those. V1, V2. So VP, it's a linear circuit. It's linear in the inputs, so I can give it a VP due to 1 plus VP due to 2. And there's also VP due to 3 and 4, but those are 0. VP due to 3 plus VP due to 4. Because whenever only 3 is on, then this VP node is grounded. And when only V4 is on, the same thing. So then we have VN here. Remember VN, we have VP always equals VN for negative feedback. V out is V out due to 1 plus V out due to 2 plus V out due to 3 plus V out due to 4. Let's do V out due to 3 first and 4, because those are a little easier. If I turn everything off except for V3, that means this node here is grounded. These two they're both grounded, so they're at the same potential. If they're grounded and I get no current through here because this doesn't accept a current, there's no current, there's no reason for any current to be in any of these, then the voltage through this entire line is 0. So everything here is 0, which means Vn is 0. And since Vn is 0, remember we were able to erase one of these branches. So then I have V out due to 3 is just V3 times the gain term, which is negative RF over R3. So the same thing for V4, negative RF, R4. Okay, so now 1 and 2. That's when these guys are turned off. So I'm going to ground these. But notice what happens when I ground these, and might as well ground one of these. So let's look at this bottom node first. This guy right here. It's critical that I have this resistor and whatever resistance I have here in order to determine the gain term that V1 is going to see. So R3 and R4 are in parallel. So how do you write parallel? Well, it's an effective resistance. It's the sum of 1 over each resistor that's parallel. So in this case, it's 1 over R3 plus 1 over R4, which equals R3, R4 over R3 plus R4. And we're going to call that R34. So I have R34 right here, and it's grounded. Remember I said up here on VP, we're going to consider VP due to 1, VP due to 2, and so forth. So we have V out due to 1 is equal to VP due to 1 times the gain term that would typically be seen at that node. For putting an input on that node, we're just replacing V1 with VP1. In the case when we did the non-inverting summary, it was just V1, but now it's VP1 because that's what value is seen at the VP input. So it's whatever is seen at the VP input. That's what we're looking for. So VP1 is seen at the VP input, and that's what sees the gain, 1 plus RF over R34. Then we have V out 2 is due to the source on the 2. Then that's going to be the same exact gain term. Now, notice that these are identical gain terms, but the VP1 and VP2 are different. So what are these VP1 and VP2? V1 is a source that gives us the highest potential here, and then we drop potential across here, and then we drop more down to ground here. So I know that there's current flowing through this entire set right here. I have current flowing through both resistors because of this V1. I know that I have no current going through here, as usual. So whatever amount I'm trying to find here is the voltage that's dropped across R2. V1 is being divided, and it's always the voltage across R2 divided by the total resistance in those series resistors. So then the sort of same argument for VP2, except now it's going to be when V2 is on, and we have R1 this time that remains. That's the voltage across R1 to ground, and then it's R1 plus R2. I wrote R3 over here. So now we have these VO1. VO1 has whatever is seen on the non-inverting node times the gain, but that value that's seen on the non-inverting node is actually this value here that's being divided. It's the actual input that has a divided value on it. So we're depleting the inputs already. So we have to compensate for the depleted input on the gain term. That's just how it works for a non-inverting amplifier. The non-inverting input, if you do superposition on the inputs, then you get these dividers out there on the front. Alright, so that's pretty much all that I want to say about these circuits. Good luck.